Значит, у меня есть, я буду рассказывать, конечно, таким слайдом, который у меня в какой-то момент закончится, я начну их просто писать. Но первые несколько слайдов у меня есть. Значит, курс посвящен введению в квантовые группы. Значит, стандартная шутка здесь, что квантовые группы – это не квантовый объект и не группа. Значит, не группа, а кто? Это мы еще будем обсуждать. Значит, что означает не квантовый? Значит, здесь слово квантовый, то есть, квантовая группа – это, где слово квантовый стоит вместо слова, как синоним слова деформация. Это деформированный какой-то объект. Так, грубо говоря, так, приблизительно, в кавычках группа, не совсем группа, но вот, значит, то есть квантовые науки, и можно думать, как некоторые деформации классической. Другое дело, что в квантовой группе в каком смысле деформируется тоже уже сразу же квантовый объект. Но это вот тонкости. Значит, и вот как объект это в алгебре обычно алгебра. Значит, и вот сейчас я некоторое время говорю о деформациях алгебры. Деформации, значит, у меня будут рассматриваться формальные. Значит, вот пусть у меня есть какая-то алгебра А0, и я сразу же предполагаю, что она коммутативная. Значит, h – это формальный параметр, то есть у меня все будет в рядах над h. Часто можно ограничиться полиномами или там еще как-то. Сейчас у меня ряды. Значит, формальная деформация, значит, это алгебра, которая, значит, как векторное пространство, это исходное А0 тензорно умножить на ряды от h. Я здесь написал c, там может быть r, про основное поле я не очень буду смотреть серьезно. Значит, в которой как-то изменено умножение. То есть в этой алгебре А у нас есть новое умножение, вот я его назвал буквой звездочка, который, значит, устроен так, который имеет такой вид. А звездочка b – это вот исходное умножение, вот тут у меня даже, я не знаю, мелко написано точка, что вот это исходное умножение в алгебре А. И плюс поправки. H бар умножить на какой-то μ1, плюс h квадрат умножить на какой-то μ2 и так далее. Здесь вот эти А маленькое, Б маленькое – это элементы алгебры А большое. И, соответственно, μ1, μ2 и там μ3 там, и выше – это функции из А0 тензор А0 в А0. Я неправильно сказал. А маленькое, Б маленькое – это элементы исходной алгебры А0. И умножение предполагается, как-то говорится, h-бар линейным. Но h-бар – это как бы константа. Можно думать, что это маленькое число. То есть если вы хотите умножить элементы не А0, а какой-то А0 умножить на h-бар, значит h-бар вынесется. И все умножить. Вот. Значит, эта деформация, она уже может перестать быть коммутативной. Вот слово коммутативное я даже здесь выделил. Но еще должна остаться ассоциативной. Значит, и условие ассоциативности это семейство уравнений на вот эти μ. Если вы его напишите, то условие ассоциативности, что это А на Б на С равно там наоборот, видно, что оно будет так примерно квадратично по μ. Оно, можно сказать, просто квадратично, если учитывать, что вот есть у нас здесь оператор μ0, который есть просто А умножить на Б. Не знаю, неважно. Значит, то есть мы берем, пишем ассоциативность и разлагаем в ряд по h-бар. Значит, в нулевом порядке получится ассоциативность исходной алгебры А0, а в первом порядке получается вот, например, такое уравнение. И там я как-то перенес все в одну часть, и я надеюсь, что я не ошибся. Вот. Значит, здесь мне написано, что еще есть некоторая калибровочная свобода. Что я имею в виду здесь? Что вот когда я пишу, что А это изоморфно А0 умножить на С от H, это немножко не канонически. Это изоморфизм векторных пространств. Я могу сменить базис векторных пространств. То есть даже если у меня, то есть когда я говорю, что вот эти А маленькое и Б маленькое, давайте, раз это уже 10 раз сказал, я это напишу каким-то цветом, то есть А маленькое, Б маленькое прожит А0. Значит, но мы можем вот это вот вложение А0 в А сменить, вот заменившее а маленькое b маленькое, ну вот каким-то таким образом. То есть здесь, давайте раз запишу справки, вот эти ньюиты – это отображение из А0 в А0. А мьюиты – это из А0 тензор А0 в А0. То есть, если я по-другому определю, ну, введу образующую исходную алгебру А0, значит, у меня как бы структурные константы изменятся. Ну вот, в зависимости от этого. Ну, тут у меня уже на слайде не поместилась формула, как эти μ изменятся, если я заменю ню. Но там дальше я напишу это явно и может еще. Так. Нет вопросов?
А это преобразование обратимым должно быть, которое внизу написано?
Оно автоматически обратимо, потому что у него оно устроено как единица плюс поправки по h-bar. Любое такое преобразование обратимо.
Ну это формальный ряд, да?
Формальных рядов. Да, формальных рядов. Да. Ну или, пожалуйста, ну да, формальных рядов. Давай. Топология так введена. Хорошо. Значит, ну, в общем, вместо того, чтобы сейчас сразу начинать приводить примеры, я немножко как бы усложню или изменю ситуацию, попробую выговорить геометрический контекст, геометрический, ну, в общем, сеттинг для данной деятельности. Значит, то есть теперь А0 это будет функции на каком-то многообразии m. Ну, там, гладкий, там, бесконечный. Ну, или там можно считать, что мы решаем задачу локально, и тогда это у нас просто открытое подмножество Rn или открытое подмножество Rn и просто функция. И если мы работаем с функциями, то, естественно, считать, что μ и νu – это как бы естественные операции на гладких функциях, то есть это заданы какими-то дифференциальными операторами. Значит, посмотрим, что нам дает наше условие. Ну, мы люди простые, мы будем смотреть на μ1. И вот я просто честно с мышкой скопировал условие на μ1, вот это линейное условие. И вот я говорю предложение, которое говорит, что используя нашу калибровочную свободу, мы μ1 можем в этом случае привести к вот такому виду. То есть что здесь написано? Здесь написано, что вот b и c это какие-то функции. Ну, в общем, функции будут по-прежнему как элементы алгебры обозначать а маленькое, b маленькое, c маленькое, потому что f же h нельзя, потому что h уже занято. Ну, там h-бар занят, но мы запутаемся. Поэтому такие немножко неудобные обозначения. И здесь написан ну, такой оператор, который, во-первых, косимметричный. Вот здесь стоит weight. Ну, и это значит, он является первым порядка по обоим аргументам, и по b, и по c. Вот эти коэффициенты k и g, вот я зеленый делаю, k и g лежат в 0. То есть это какие-то тоже функции. Понятна формулировка? Это довольно сильно это все-таки сильное утверждение, то есть это μ1 это был какой-то оператор двух аргументов, то есть он может быть там 100-го порядка по первому, 101-го по второму, или еще что-нибудь. Про него говорят,
что он... не понял обозначения. Что значит, что c бесконечность от μ?
От m. Это m. Это не μ. Там m многообразие. Хочешь, я его назову x.
Хорошо, ну тогда нормально. А то как-то...
Мы типа говорим, что у нас есть вот эта свобода, да, и это типа соотношение на μ-иты не должны измениться. Из-за этого мы получили, что μ-иты сильно ограничены.
Ну, у нас есть сильные условия на μ-иты, еще есть свобода. Вот если вооружиться и тем за зубов, мы увидим это предложение. Сейчас мы его будем обсуждать. Я не буду врать вам, что я все буду доказывать на курсе. И, собственно, это предложение тоже я его, может быть, не докажу, но я думаю, В общем, я скажу что-то, что, по-моему, является убедительным. Ну,
А там стоит DIT B, wedge, DGT C, вот в самом
да,
нижнем там
да,
ряде.
да.
А эта штука, она же действует в А0, а не А0 тензор на А0. Ну, то есть мюта, они в А0 действуют просто.
Ну, да, да, и, значит, плохо написано. Давайте я перепишу. Значит, DIB, DG, C минус DGB, DI, C. Хорошо?
Да.
Ну, в общем, вместо примера мы обсудим мы, в общем, какие-то рассуждения, но сначала вот сверху у меня написана постановка задачи. Вот я еще раз скопировал уравнение, которое у меня есть. Да, но на всякий случай, да, я вижу, что кто-то записывает, то есть вы как вам удобнее, но вы можете не сомневаться, что эти слайды я выложу потом. То есть я их немножко, я исправлю ошибки, может быть, сделаю новые, но я что-то я их выложу. Значит, а теперь как устроена калибровочная свобода? Вот тут у меня, я вам обещал, и вот написана явная формула. Я тут мог... Нет, может, я даже со знаком. Ну, вообще не знаю, может быть, я тут с глобальным знаком напутал, но с точки до этого я надеюсь, что правильно. То есть что, если я, наверное, чтобы за этим проследить, надо вернуться к первому слайду. То есть я все работаю в первом порядке, то есть я вот сдвигаю вот эти А и Б на ν1, ну и тогда к μ1 у меня прибавится μ1 от А умножить на b, А умножить на μ1 от b и вычтется μ1 от АБ. Ну вот, как и здесь я и написал. Какая калибровочная свобода есть. Вот. Ну, теперь, значит, давайте смотреть. Вот у нас есть уравнение. Ну, μ это дифференциальный оператор, ну, вообще говоря, какого-то порядка. То есть можем его написать в каких-то координатах. То есть утверждение итоговое, что это дифференциальный оператор второго порядка, который первого по каждому из аргументов. Ну, можно так пытаться сверху по порядкам на него и смотреть. Ну, предположим, что вообще крайнее, что он это оператор, ну, можно даже еще более крайне, что это оператор нулевого порядка. То есть вот μ1 это b умножить на c. Может так быть? Давайте я спрошу аудиторию. Что μ1 это оператор нулевого порядка.
Ну вот в верхней формуле он удовлетворяет.
Удовлетворяет. А как это относится с предложением, которое говорит, что μ1 должен быть второго порядка?
Тогда можно, наверное, калибровочным преобразованием.
Да, можно взять калибровку тоже постоянную, там, то ли единичный, то ли минус единичный оператор, и мы эту константу убьем. Ну, это божественно. Поэтому может, и это просто мы как бы не под вопрос калибровки. Хорошо. Следующий вариант, сами видите, это оператор первого порядка. Вот пусть там есть какой-то оператор, вот там что-то, какой-то коэффициент k, b на d1c. Ну, тогда мы это подставляем сюда. Значит, и смотрим, какие у нас тут члены появятся. Значит, ну, я вот даже потом заленился, единичку в индексе не писал, это, наверное, зря. Один. Значит, ну, в общем, я подставил вот этот член, и у меня получилось 5 слагаемых. Ну, и 5 слагаемых никак не могут сократиться. То есть из них вот эти два сократятся, вот эти два, наверное, тоже сократятся, это нет.
Хорошо, а если мы возьмем линейную комбинацию?
Или я где-то тут или я кого-то не того сократил, наверное. Maybe I should switch to English. Okay, I switch to English.
Maybe we could take linear combination of such differential operators of first order, and it will be okay or not?
We can try. So what kind of terms should we have? So first of all, this is the quality of the differential operators. And hence we can, so if you look at the first order differential operator, then we should add another term for the first order, and also they should be derivatives with respect to first argument. Okay. So probably you can try to add some term like L d1b times C. Maybe something like this.
And sorry, and what means first argument?
First coordinate, if you want. We have a function on several coordinates. Let's keep.
So we just take the first coordinate. Okay.
And what? Okay, let us compute slowly, if you want. What we will have. First of all, about this computation, no questions. I have I looked and correct one mistake. Maybe there are many. I don't know. So what's the result? If this computation is correct, then what we get? The remaining terms will be KAB d1 of C. Okay. If it is so, then there's not necessary to compute this because this cannot give us first derivative of C. Okay.
Yeah.
So hence this is not important. So you can look if you have C times some differential operator, then you have some C the terms which do not have derivative of C from here. You can have such terms from here. In principle from everywhere. But here they will obviously cancel. If you don't take derivative of C, then you have just compute mu1 of A and B. So you get 0 here. And here, if you don't take derivative of C, you take some differential operator of B, AB, and then you take just some differential operator of B. So this cannot be 0. Are there any questions about this this case, first order differential operator?
I think I get it.
Okay, I can look to your faces and see whether you're satisfied or crying, or maybe like my daughter. I don't know. Okay. Here, so we discussed inverts the differential operator of the zeroth order. Now we look to differential operator of the first order. I skip second order and now go to the third order and consider somehow a bit special case, but I hope it's still okay. Case where we have term like this, d1, d2b times d3c. Special means that I assume that all these numbers 1, 2, 3 are different. Okay. If you want, then we can consider a case where some of them coincide. So of course, it's not, but I think this case is good for start. So assume that we have such term. What is exceptional about number 3 and higher numbers. Then in this equation, we'll have terms where all functions a, b, c are where we take derivatives of all these functions a, b, and c. Of course, not from here and here. Here we have a and c without derivatives, but from middle two terms. For example, from here we will get, I write in green, we will get something like d1a, d2b, d3c, and also d2a, d1b, d3c. We will have such terms. No, maybe I switch color. In order to cancel such two terms, which we have from here, we need to add terms to mu1, which should come from here and cancel this. And I wrote them in blue. Okay, so the only way to cancel these two terms is to realize that actually in mu1, so our equation on mu1 leads us to the fact that we should have these also these two terms with the same coefficient k. Then we argue that if we have these two terms, then we will have additional terms with, again, with all derivatives which come in from here. So since here we have d2, d3c, so we will have not just this term d1a, d2b, d3c, but also term where in opposite sort d1a, d3b, d2c. Hence, we have to add terms which I wrote in green color, which lead to the required wanted terms from the here, and so on. So arguing like that, we see that if we have such term, then we will have this sum of this form. All three possible terms. So we have three derivatives, 1, 2, 3, and we should decompose them. 2 should act on the one argument, and the remaining one to the another argument. So we should have all 6 terms of this sort. And only in this case we will cancel. Our equation cancel. And this combination is now wanted in the sense that if we take nu1 equal to this, maybe with minus, maybe without, then we get exactly this summand. So if we have such third order term in mu1, then we can cancel it using our gauge freedom. And here I actually use the fact that this is a third order differential operator, not first.
May I ask you a question? What we consider manifold and no, we use local functions or global functions?
If we study C infinity, then we have how it's called decomposition of the identity. Any function can be realized as a sum of function with which local support near in some neighborhood of the point. So it is not very important.
Okay.
But if it is more safe for you, you can think about the C infinity of Aram. Okay. Other questions? So if maybe for the full proof, so there is one point which is skipped, which is inverse. So we don't, if we cannot have in mu terms like d alpha b times c, where we don't have the derivatives of one argument. So, and if we have derivative of both arguments and this operator for at least 3, then it has to be cancelled. It can be cancelled by mu. This is a matter of Okay. So now return to our.
Сейчас, то есть полная производная убивается калибровкой, да? Это ты сказал.
You're asking about this remark, or
Yes,
this?
yes.
Here I said if we
Yes,
don't
about this
take
remark.
derivative of the one argument, this argument, this is a generalization of the first or maybe second bullet. Like here, if we don't have derivative of the b, then it doesn't matter what we write here. What is L? We cannot have 0.
Мгм.
Okay, now let's turn to geometrical setting. So again, our initial algebra is the algebra of the smooth function on some manifold. We have star product, which is product with some corrections. And we already explained that mu1 should have, you see here, I copied the formula, which is not good. So I correct it. So this is a formula. This is for mu1, and let us compute one more thing. The second term, h squared term, and this is not important, but for the matter of composition, I compute the something like Jacobi identity. So we know that product star product is associative. Therefore, this Jacobi identity, Jacobi, I don't know, Jacobi combination should be 0. So here I computed for the star product and look for the h squared term. Okay. H squared term is the first non-trivial term in this combination, since the commutator, a star commutator is in the first non-trivial term is just a star product in the zeroth order of h. Is the ordinary product. And ordinary product is commutative. Hence, a star commutator in zeroth order is 0.
So, what is star commutator? Can you please repeat? It says a star b minus b star a. Yes.
Yes.
Okay.
So this is what I'm saying. And mu1 is the first non-trivial term in this star commutator. And the fact that this is 0 leads to the fact that mu1 satisfies the Jacobi identity.
And mu1 is obviously skew symmetric.
In this formula, yes. At this point, I hide because there are, I don't know, somewhere here. So you see here, I can look to the operator of the first order, operators of the third order. For operators of the second order, I also have gauge freedom, and this gauge freedom cancels symmetric part of mu1. So mu1 can be of the second order, can be some of the symmetric and antisymmetric part, but symmetric part is cancelled by gauge freedom. And for example, one can argue that this term is do not depend on the gauge freedom. So actually, this mu1 is well defined without this theorem. And the result of this line of arguments is that mu1 is a Poisson bracket. So this is a operator which is linear with respect to each argument, each of these two arguments, which is it is derivative of the first order with respect to each of these two arguments. It is antisymmetric, and it satisfies the corresponding bracket satisfies the Jacobi identity. So this is a Poisson bracket. Okay, now we'll see how or maybe more of my slides looks like. So in this slide, I plan to recall the definition of the Poisson algebra and something else. So A0 is Poisson algebra if there is a bracket is A0 0 to A0, which is which is a Lie bracket and derivative. So what should I write? I should write a bracket of AB is a minus a bracket of BA. I should write that bracket of ABC is a bracket of ABC plus B bracket of AC. A0 is commutatives. I can write in any order product, but I prefer this one this way. And what else can I write? And plus Jacobi. And before we showed that if we consider deformation in this geometrical setting, then in first non-trivial term we get Poisson bracket. So Poisson brackets are responsible for the deformation of the algebra of function on the smooth manifold.
Any statement about the center of this Poisson algebra?
No assumption. Why do you ask?
I mean, because it's usually consists only of constant functions.
Why? If it is symplectic manifold, then it consists of the...
Yes, of course, but
you know, examples for Poisson algebra have actual sets, and we will come to it in 2, 3 or 3 slides, of course. In the proof, I use the fact that we have differential operators and stuff like that, smooth manifold. I can standard in general definition in this case given as follows. So if A0 is Poisson algebra, then deformation, or maybe it's better to say it formal deformation, of, I use zoom in order to improve my way of writing, of the Poisson algebra is again is the algebra A, which is with star product, and on the first slide such that A star B minus B star A equal to 2H bracket AB plus low terms plus, how to write this, of H squared. So the main message which was on the previous slide, that if we want to consider some deformation of algebras, then the classical counterpart of the story would be Poisson story. And actually Poisson, not necessarily symplectic, for example. Let me recall this, if probably that. Okay, I used X for manifold, or I used X, but here I will use M. M is manifold if there exists a pi. If okay, in short, it just should kind of say that if C infinity of M is a Poisson algebra. In coordinates, it is stated like before. So we should have pi, which is sum of some pi j di times dj, and the bracket of two functions f and g is the sum of pi j is given by standard formula, which I don't know where to write. It is not difficult, but maybe not absolutely obvious that any Poisson structure on the algebra and functions can be written in such way. If you can I leave it as an exercise, or you can think about this definition, coordinate definition, as the actual definition of the Poisson algebra. No, so this statement means that Poisson bracket depends only on the differential of the function, not on the function itself. And then it's written in this form. Okay. Now I want to stop a bit from the general discussions and come to some examples, if nobody minds. And first example which I want to consider is a constant Poisson bracket. So my algebra will be algebra function on some variables x1, so xn, and the bracket will be constant. So bracket of xy and xj will be epsilon ij, where epsilon j is a matrix. Matrix constant with scalars. So in principle, brackets of two coordinate function can be some function. Here I take scalars. Of course, we have some conditions on the scalars. So first condition is that our bracket should be antisymmetric. So epsilon ij should be equal to minus epsilon j I. And the second condition is a Leibniz rule, but Leibniz rule here means nothing because I use it as a definition. I define the bracket of the coordinate function. If I want to compute the bracket of two functions like which are polynomial, then I use the Leibniz rule. And third thing is a Jacobi formula, Jacobi identity. It is a sum of three terms like this. But in this case, since bracket of the, again, I check it only for coordinate functions. And for coordinate function, this bracket is constant, therefore this bracket is 0. Hence, everything is satisfied. I don't know whether it's convincing, or maybe there's some other more simple argument. Okay, are there any questions about the constant bracket? So I'm saying that if epsilon and j are constants, we don't have any equation. In principle, equation that's mu some pi or mu1, which is a Jacobi identity, some quadratic equation, this coefficient epsilon ij here is a constant, or pi j in this formula, or I denote them by kij even before. So this is some quadratic relation differential, not obvious, not trivial to find. But if they are constant, then any constant work. Okay. Okay, if no more questions, then we come to quantization. And for quantization, just for simplicity, move a bit lower and consider a case where we have two variables, say x and p. So instead of x1, xn, I denote by x and p, with the bracket x and p equal 1. And we want to quantize them. And it is, I mean, probably many of you know that quantization of this would be, let me write it in some, again, green color. The quantization of this will be something like commutator of x, if you want, and p will be, or some number, or maybe h bar, stuff like this. And this is what I'm writing here. This formula is sometimes called Moyal product, or maybe somebody knows another name. So what's written here? That if I take two functions f and g on x and p, and their product is given by the following formula. I take their tensor product, I apply this differential operator for them, and then m is a multiplication. M is a multiplication. If you want, as an example, I can take, say, x and p. X. Let me write heads. Maybe it will be better for everybody. Or maybe not. Maybe not. So I instead of heads, I will write star product. So I take two functions, say x and p, and compute star products. So what we will have? We will have m of first term will be x tensor p. Second term will be 1/2h dx tensor dp minus dp tensor dx applied to x tensor p, and so on. But other terms are 0 because we have started from linear functions, and other terms will have more. We'll get 0 after differentiation. Okay, so, and this is equal to what? This is equal to, let me move a bit. First term is xp, and second term's 1/2 h bar. And if I compute px in opposite order, then I get, I don't know, maybe I ask audience, who knows what I get?
xp minus 1/2 of h bar.
Yes. And this is consistent with what I wrote in green. What to do? This is okay. This is not a proof of the fact that the star is a associative product, but I need to have some problems for you, and probably you also need to have some problems just to follow the lectures. So I left this as a problem. Show that star is associative. Are there any questions? Probably you're not
why this formula is so complicated? I mean, compared to commutator of x and p equal to h bar.
Because it works for any polynomials. There's a formula for commutator of x in power n and p power m, something like this. And not commutator, but actually product. So if I don't know.
I see.
I agree with you. I don't like it. But
so this is formula for normal ordering, yes?
Yes. Sometimes people write not just moil, but moil while. Or wheel. I think wheel.
So this is so complicated because we work initially in the commutative algebra, and we have to put anything in some normal order, yes? And our commutative monomials are, in some sense, assumed to be normal ordered as non-commutative. I see.
Exactly. Good explanation. Okay. You see, I wrote the difficult formula for the simplest case where epsilon hj is 2 by 2 with only one, with non-trivial entry equal to 1. Do anybody have any suggestion what to do for generic epsilon hj?
What is the question?
How to write quantization for formal deformation for generic epsilon hj?
Maybe choose of coordinates will solve the problem. No.
What kind of coordinates?
Maybe.
Poisson.
Yeah.
We can we can поменять матрицу на косимметрическую, ну, можем диагонализировать матрицу, ну, привести матрицу к виду 1 минус 1.
Okay, for any epsilon j which is antisymmetric, we can change our basis and move it to the form. There are several standard form for antisymmetric matrix, but for example, like this.
And even we can change it globally.
Here,
not
our
globally,
bracket is
but-
constant. There is no question of globally. We take linear transformation.
Okay, of course.
Global.
Yeah.
No. The analytical questions. There is no global Darboux coordinates. Just to be sure, there are local only. But here we work for the constant bracket on the local on the run. So there's no questions actually.
Okay, no question. Yeah.
And so epsilon j is like this, and hence we just use the formula of the previous type, just how to say it, make non-commutative x and p in different way. Okay, maybe I said wrong, but I hope everybody understood. Just work for each pair xi and pi, we work separately by the previous formula. Okay. Okay. We come to next example. Yes. Which is here we didn't have full title, but I write it. And next example is a linear bracket. So what do I mean? So again, I have something wrong with the spelling. Okay. No.
Maybe bilinear bracket.
In opposite sense. So what I mean that we again I can take A0 to be some C of, I forgot how to write which kind of brackets here I write. Okay, I can write polynomials, for example, some variables x1, xn, or doesn't matter. So, okay, right here, different if here's and now the bracket between coordinate function xi and xj will be equal to epsilon ijk xk. Some of k, where this epsilon ijk are constant. In terms of our first slide, here we have pi ij, and the first example, this pi ij were constant, and here this pi j are linear. In this sense, this bracket is linear. We have obviously we have a conditions on this epsilon ij. First condition is antisymmetric condition, so epsilon j is equal to minus epsilon jik, and we also have Jacobi relation, and this leads to the fact in this case if we substitute this epsilon ij's, we don't have it will be algebraic relation on this epsilon ij. Will be of course epsilon j are constant, so we can't have derivatives, and result we have the Jacobi relation will be lead to the fact that if this epsilon jk are structure constants of some Lie algebra. If you can think that this xi and xj form a basis in this Lie algebra, and this is almost obvious. So I take this Lie algebra. Maybe I denoted of the Lie algebra. Maybe I denoted by G is a vector space generated by x1 and so on xn. And our Poisson bracket preserves the space. We start from any linear function axis and obtain the linear function in axis. And therefore, the Jacobi relation for the Poisson algebra leads to Jacobi relation of this Lie algebra. So this case is different from the previous one. Not any epsilon works. The Jacobi relation is indeed a relation. It's trivial. What can I do? But there are solutions to this relation. More geometrically, so what we have dual space to Lie algebra G star, and our algebra A0 is a algebra function of this G star. So this G, and this algebra is Poisson algebra. So G star is Poisson manifold.
Well, maybe technically it's just the algebra of polynomials on G star.
It depends on what I write here. But I don't have sloppy with notations and all of the stuff. By the way, other questions? Okay. If we, but I agree with Pasha. Algebraically, we can think about polynomials. So take A0, not just algebra function, but algebra of polynomials, or it will be, if we take A0 to be algebra of polynomials, I don't know how. Or another way to write it is a symmetric algebra of the G. Think about G as a vector space. And now we want to quantize it. So we have Poisson algebra, and there's a question of the quantization. Who knows what we'll have as the quantization of this algebra?
We will have universal, универсальное обертывающее.
You suggest to take universal enveloping, and of course this is correct, but in our definition, the quantization should depend on h bar. Where is h bar in universal envelope?
We have add h bar in commutation relations with right hand side, in right hand side.
First question will be, what is a vector space? And what is a
is the same. It is as this point of G.
So we have A0, and we are talking about quantization. So let me write it maybe in following form. So S of G is as an algebra, it is a tensor algebra of G modular relations at x times y minus y times x equal to 0. And the quantization, as experts suggest, should be related to universal envelopment, which is a quotient of tensor algebra by the relation x times y minus y times x minus commutator of y and x equal to 0. Okay.
But we can multiply the
You suggest to write to add h bar in this formula, so somehow maybe here.
yes.
And this again, I agree that this is correct, but again I bit disagree because this is a formula of this type, and formally we're asking about formula of this type. So we should take some space, like I don't know, s of g times c of h, and define the product in this space. Or even I don't know how to say it. So our desired relation should be of this form with h bar. But what is our space? I don't know whether the question is clear. Are there any questions on what we are doing? Okay. Can you hear me?
Yes.
Okay. Just for safety. Okay. I give some sort of answer, but you can think about it again. Is it some trick? And if you don't like, you can ignore it. But because the morally, the answer is universal enveloping. This is clear. But standard approach is the following. So we take u of g and consider it has a filtration. So there's we have u0 contained in u1, contained in u2, and so on. And u0 is just c, u1 is a c plus g, u2 is a u2 is not so easy to write. U2 is a combination of terms of order non greater than 2. So this actually filtration. So instead, contrary to symmetric power, here we don't have grading. Linear difference of two terms of order 2 can be term of order 1. But
so I have a question. Why we should write h bar in front of the commutator? It is ну как бы он же сам первого порядка по h bar. It is of himself of the first order of h.
Again, let me remind, what do we mean by quantization? We want to define a product on the space which I erase. Okay, let me return. We want to define a product here, green product if you want, such that the first h bar, first non-trivial term in the commutator, so x y minus yx will be. I struggle with 2's, so just don't complain about this. Will
2
be
h bar.
h bar plus O of h bar squared. And this is what we with Sasha wrote here. Maybe again, I'm struggling with signs. But
Yes.
as usual, the only thing to correct signs is do it yourself. Okay.
May I suggest some formula which I think that it is no, in this case is right. Maybe we should write something like exponent, but to exponent we should add linear component. No. For example, may I? Is this true?
I don't know. I will somehow circle this problem. You will see. I will not write a formula. I will solve the problem another way. Go around it. Anton, do you still have questions or no?
Да-да-да, ну вот как бы с обозначениями непонятно, потому что обычно коммутатор, он как бы равен в первом порядке h-бар на скобку Пуассона, поэтому он сам по себе первого порядка по h-бар, и вроде как никакой h-бар тогда ставить не нужно. Ну, как бы вот, вроде как-то так принято.
This commutator is a commutator in Lie algebra, so this is a linear term. Linear x and y. So usually in universal Belpin, this h bar is said to be equal to 1. If h bar is numbered, so the algebra doesn't depend on this number because we can hide it in Rascalian variables. If h bar is not 0, of course. If h bar is 0, then we get symmetric algebra. But I suppose that I'm answering, I don't misunderstood question. But if my answer works, then I will go.
So no, it's not so serious question, but
Okay, let's ignore your question. I'm happy. Now I want to recall the BW theorem. I don't know where to do this, so which says that un plus 1 quotient by un is an n plus 1 symmetric power. So we have a algebra with filtration, and we can take associative grading as associative grading with respect to this filtration. So it will be direct sum of un plus 1 quotient by un. And PBW theorem says that this is isomorphic to the sum of Sn or symmetric origin. And now I define what is called Wreath algebra. As follows. Maybe I even look to some place to write it correctly. Maybe. I wrote it in this slide, but of course I need more space, so I go to next slide. maybe okay. So what I wrote here. So this algebra consists of the combination of the form Q0 plus H bar Q1 plus H bar square U2, so probably infinite, but such that degree of Ui is less than equal to I. And this combination should be finite in the sense that how to say that degree of I is bounded. And this is the algebra. Maybe I write it. So we have U1 times constant, then we have U0. This is U1, which is greater. This is U2, U3, and so on. If I take this is closed under multiplication. So if I take two terms of this two combinations of this form and then multiply them, then I again get the expression of this form. This algebra is a vector space. This A is as desired as a symmetric power times series on H.
Do we really need this power series in H? Because it feels like we get, for example, from each of the summand, we get the 0 degree U, which we can multiply on H. So we need to like set them equal to each other.
I agree, but we need, because here, so this is sum means that we can take only finite sum here. And this power series means that we can take power series. So we can take terms of U0 and multiply it by some infinite power series. And we cannot obtain this term just from here. Okay? So we cannot have a term like U0 times 1 plus H plus H squared plus and so on if we do not add this power series. If I use not power series but polynomials, then it will be unnecessary. And actually, this fact that here the direct sum is somehow hidden here. But you can look at this as an algebraic some trick and just to say universal enveloping in some formal word and ignore it. But you can look at this. So the generators of this algebra A as a vector space. So as I wrote here, how to write this? I need to take the generators of this A as a model of a power series. Will be what? Will I take generators of U0, then I should take complement of U1, complement of U0 and U1 here, complement of U2 and U1 here, and so on. Here will be leave generators. Right. They're not canonical. But it doesn't matter. if I take here they're still at least canonical for U1, we have decomposition of constant and Lie algebra. And if I take two terms here, two elements of Lie algebra, compute their product, I come here, compute their difference. The second order term cancels, I come here, I divide over h, I return here, and this will be my bracket, my initial bracket. So so this trick with Wreath algebra is how to come from the universal envelopment, which is of course a deformation of the symmetric algebra in the natural sense, to the language of the formal deformations. We should take a copy of algebra many times, infinitely many times, because we need to have such copy because we work over power series, and this power series somehow helps us with the formula. The explicit formula, which Sasha you asked, hidden is the choice of generators. I don't write the generators of. If I want to write the formula for the product x and y, I need to pick some complement of u2 to u1, and I hide this. So I didn't pick this complement explicitly, so I don't have explicit formula. Okay, is anybody wants to ask the question? Okay, it's already 30 minutes. So I plan to stop soon, I think, because nobody can listen too much online, and probably in principle I raised the idea and I followed that such course, online course, is more similar to reading a book than to, I don't know, actual course. So I give you some references and I plan to answer to your questions in this meeting. But initially, my idea was to make the lectures short, and I will do my best. So maybe we just skip the next slide, which is important, but if you want, you can read it here, or I will send you my slides, or in the book. And this slide with general results, I will write it better, but it should state here are two statements and one problem. And I will not write it now, just not to finish shortly. But HKR is a theorem of Hochschild, Kost, and Rosenberg, and this is a general theorem from which fact which we proved on the second slide follows. So what is this theorem? So we have some mu2, mu1 on the first slide, and the condition which we have for mu1 is actually a condition that mu1 is a representative of certain cohomology, Hochschild cohomology. And the theorem by these guys, Hochschild, Kost, and Rosenberg, says that actually any representative of the Hochschild cohomology is a polyvector, for the case where the algebra is algebra functions, is a polyvector field. For example, for second Hochschild cohomology is a bivector field, antisymmetric. So this is what we proved on the first proposition, and this follows from this theorem. Next item, I want to say you that for in geometric settings there is a theorem by Kontsevich, which we will not use, of course, and we will not prove, and actually we will go a bit another direction. But there is a theorem which I want to mention, that any Poisson structure can be quantized formally. For case of symplectic manifolds, it was proven before Kontsevich. By Fedosov and others, there are several proofs. the most, I don't know, physical case where a manifold is T star of some x is obvious by the same line as we wrote for universal envelopment, or maybe even more. For general symplectic, as was proven by before quantization, by Fedosov and others. And this is quite difficult theorem. There's now other proofs, Tom Arkin's proof, other, but it's actually a very difficult theorem, and is not, the proof is not essentially not algebraic. For example, it works over it doesn't work over rational numbers. In quantization formulas, there are somewhere some zeta values and some stuff like that. It's quite exceptional result. And in algebraic settings, this is not true. So there are, I mean, I read in books and that there are examples of the algebras, Poisson algebra, which cannot be quantized. And I wrote as a problem to find such example, maybe using literature, and explain it to me. This problem will start, it's not for some extra points. Okay. In this slide, I will write example of T star of x, but okay, if I want to finish, not now. And probably I will want to add a bit more information, but I will add it. And here I write some, this is the last slide, really last slide with some details about reference and organization. So in the middle, you can see the website, and maybe I can write it to chat. It will, if it will be better.
Yes, please.
For audience. And I repeat that if you want to receive some information about the course, please write your in chat to all everybody or to privately to me your email, just not me to him. And here I just try to print it, not write by my way. Here I put some references. So my two main references for the at least first half of the course, and maybe for the whole course, will be two books. One book is by Ettinghoff and Schiffman. It is called something like Introduction to Quantum Groups and stuff, but they have only one joint book. This you can find by authors, and another book with the same by Charin Presley. And the reference for the Kontsevich theorem and some context is his paper, Deformation, Quantization of, and something. Of Poisson manifolds, I think.
Is it readable?
It's not bad. It is difficult, but not. I mean, this hard result, no, but it's not bad. It is not. It is not like I know. Kontsevich Soybeman papers of 200. No, it is just without courses. Okay, and two more points here. First, or maybe second, that next week will be no lecture. So we stay, and actually we start to go to quantum groups. You see, today we have no quantum groups, and I would say we are not very close to them. But we will not have quantum groups in 2 weeks, but we'll come much closer. We will actually study Poisson classical counterparts for quantum groups next time, but next time will be not next week, but in 2 weeks. And the question is, are there any problems with current time? So according to schedule, our lectures fall 12 to 13:30. I'm a bit over time already. But if are there any suggestion to should we move sometimes 1/2 hour before, 1/2 hour later?
I have a suggestion to move half hour before. If it is comfortable for other audience.
There is a course held by Krichiver.
Maybe it can be also moved, but I don't know. Other. Of course, we cannot be at the same time with Krichiver course. Of course, big intersections.
And how are you supposed to pass this course?
I give problems. In this lecture, we have actually one problem. Maybe after I write the slides, will be more, two, like this. And when we come to quantum computers, it will be probably more, and you have to solve problems. And we discuss solutions.
Okay, thank you.
Maybe at the end of the course, I will suggest to start to some small theoretical, I don't know, tests about general notions, but it's not very probable. I don't know. It depends how it works, but this I mean, special course for almost experts. So maybe you know better than me how to study. Okay, then I stop recording. Yes, and that's it for today. Thank you for listening.